This is going to be the first of a few videos that I'm going to make to cover the OBD2 system that became mandatory in the United States in 1996 and later became mandatory in other countries around the world and became known as the global OBD2. What I'm going to be saying is what the law requires, and what you're going to find is that a lot of things that I say, or not a lot of things, but some of the things that I'm talking about, you're going to find that, wait, this is not what you found to be true in the cars. So the manufacturers have got away with doing things that don't conform to the OBD2 requirements. I'm not sure what's going on with that, but just know that this is what the law says and not necessarily what you're going to find. But at the same time, most of what I'm talking about is what you will find on the vehicles. So onboard diagnostics generation 2, let's get started. Some of the terms that you'll need to learn as we go through this, or at least need to understand, is FTP. You'll hear me make reference to that acronym several times, and that is the Federal Test Procedure. The Federal Test Procedure has to do with the requirements for any manufacturer to be able to sell a car in the United States. That car has to run clean. And it's going to be put into a room, it's going to be sealed, they're going to measure the hydrocarbons coming off that vehicle. If it exceeds a certain level, it fails the test, they can't sell it here. The fuel tank has to be sealed up, and they're even limited on some of the plastics and rubbers that are on there. As they're curing, they can only have so many hydrocarbons coming off there. They're going to put the car on a dyno, they're going to check it from cold start, idle, hot, wide open throttle, and all loads in between there. They're going to average those readings out. The readings have to be below the federal standard, or again, they can't sell the car in the United States. Also going to make reference to ARB, Air Resource Board. This has commonly been referred to as California Air Research Board. I'm guessing that they dropped the California because there's now 13 states that have adopted California emission standards. There is a program that runs in the background. This is going to be like an antivirus software on your computer at home or on your laptop that is watching things that are going on. As you're driving the vehicle, there's the engine computer that is controlling the timing, controlling how much fuel is going in. It's making sure that the engine runs smooth, runs clean. This task manager or diagnostic executive, it's two different names for the exact same application, is going to be running in the background, watching what's going on, running tests to make sure that the vehicle is still running clean. The only time you're going to know that something happened is when the check engine light comes on. That's because the task manager found that there's a problem. The car's not running clean. We're also going to be talking about a trip or a drive cycle. The purpose of a trip is for the task manager to check all of the inputs and set the readiness monitors to complete. If you used a scan tool with the global OBD2, one of the options on there is readiness monitors. That's going to tell you that this test was complete. If you're living in an area where they're doing emission testing and they do the OBD2 test, that's one of the things they look at is readiness monitors. The reason they do that is because people will drive around for 18 months, 19 months or more, however long it is between emission tests with their check engine light on. They know that, hey, if the battery goes dead or if they disconnect the battery, it takes a day or two for the light to come back on. So they think that if the light's not on, I can go in and get an emission test and pass. But when you disconnect the battery, clear the codes, it also resets all the readiness monitors. And so when they take it into the emission test station, they look, readiness monitors are not complete, you need to go drive the vehicle and then bring it back for a test. The enable criteria has to do with the conditions for the task manager to run the test. It's going to test the catalytic converter, but it's going to use the oxygen sensors to test the catalytic converter. It's going to test the oxygen sensors first. If an oxygen sensor test failed, or if the oxygen sensor test got interrupted because you suddenly had to accelerate, decelerate, brake, whatever, it won't try to run the test again on that drive cycle or on that trip. If it doesn't test the oxygen sensor, it won't test the CAT. Comprehensive Component Monitor is the task manager testing every sensor, every system on the vehicle that can affect emissions. When we get to looking at mode 6, and this will be on one of the later videos, there is a TID for test identification and CID component identification. History of OBD1. California Air Research Board in 1985 developed the standard for OBD1. For the most part, California's OBD1 was GM's system that they had introduced prior to that. It's primarily looking at vehicle having a check engine light, being able to set codes, being able to store codes. 1985, CARB at that time developed the standards for OBD1. 1988 and newer California vehicles had to be OBD1 compliant. The reason I'm stressing this is because when you talk to a lot of people, they will say anything pre-OBD2 is OBD1. It's not. Most of the vehicles were not even OBD1 compliant. Where this is going to make a difference is if you're working on an 88 through 94 vehicle, if the emission sticker says this vehicle conforms to U.S. EPA regulations applicable to 1988 new model vehicle, that's not a California vehicle. It's not necessarily OBD1. It may be, but may not. If it says this vehicle conforms to U.S. EPA regulations and State of California, 1988 through 94, then yes, it is going to be an OBD1 vehicle. Would monitor the oxygen sensor, would monitor the EGR valve, would monitor the evaporative purge solenoid, and it had to have a MIL, which is the check engine light or service engine sim light. It didn't cover catalyst. It didn't cover the EVAP system for leaks. And then this term, I like insufficient sensitivity to detect significant malfunctions. Taking a look back at here. The oxygen sensor. So on the GM vehicles, they had a code 44, lean exhaust. Code 45, rich exhaust. Code 13, dead oxygen sensor. For the code 44 to set, your O2 sensor voltage had to drop below like 150 volts or 100 millivolts, not 150 volts, 150 millivolts or 100 millivolts, and stay there for like 30 seconds. Or voltage went above 850 for 30 seconds or so, and now it's set a code for rich exhaust. The oxygen sensor had to be completely dead before it's going to set an oxygen sensor code. And oxygen sensors degrade slowly over time. The EGR valve, the way they monitored that is they had a temperature switch on the intake manifold side of the EGR valve. Your EGR passageway could be 90% plugged off. When the EGR valve opens, it gets hotter, the temp switch flips over, and the computer says, hey, 2 thumbs way up, system's working. On the EVAP system, you could remove the entire EVAP as long as you left the purge solenoid. The computer said everything was good. That's your insufficient sensitivity to detect significant malfunctions. In 1990, the government directed the EPA, so government being Congress, directed the EPA to develop regulations pertaining to onboard diagnostics. What California did in 1985, the feds did 5 years later. What California enforced in 1988, the federal government enforced in 1994. So all 94 and newer light duty, so this is less than 85 or 8500 GVW or less, have to be OBD1 compliant. 96 and later, OBD2 had to be OBD2 equipped. Take note of the equipped. Then 97 and later, light duty trucks, again 8500 GVW or less, had to be OBD2 equipped. It wasn't until 1999 that the vehicles had to be fully OBD2 compliant. If I remember correctly, it was Toyota who had the claim that they had the first fully OBD2 compliant vehicle in 1997. Then by 99, everybody had to be fully OBD2 compliant. In the state of Washington, I was involved with the emission test program. As they were doing the OBD2 test, the vehicles that they had by far the most problems with were the 96, 97 OBD2 vehicles because they were a hybrid system, partially OBD1, partially OBD2. Identify the component as it degrades. Standard here that they're looking at is 1.5 times the FTP. Whatever the standard was for that particular year, but let's say they were looking at 6 grams per mile. 1.5 times 6 is going to be 9 grams per mile. So by the time your vehicle is emitting 9 grams per mile, it has to illuminate the MIL and set a DTC. That is how they're going to alert the driver to the need to maintain or repair the vehicle. The standardized DTCs, so prior to OBD2, each manufacturer had their own codes. Most all of them were a 2-digit code, a 2-number code that could be flashed. With OBD2, now they're a 5-digit, not a 5-number, but a 5-digit code. And some of the codes, or most of the codes actually, are standardized. It's a P0420, a catalytic converter degraded. It doesn't matter if it's a Toyota, a Jaguar, or a Ford. P0420 is a degraded catalytic converter. Second, had to be able to access the information with a generic scan tool. So this was, I think, pushed by the aftermarket because manufacturers were going with their own specific scan tools. If you have an independent shop that is trying to work on everything that comes through the door, if they're going to work on Mercedes, they needed a Mercedes scan tool. They needed a Volkswagen scan tool. They needed a Toyota scan tool. They needed a GM scan tool. Now, there is one generic scan tool, the global OBD2, that works on everything 96 and newer. Keep in mind, if you go and get a OBD2 scan tool, this is only dealing with emissions. It's not going to talk to the computer that's managing the HVAC system. It's not going to talk to the ABS computer. May not be able to talk to the transmission computer if that's a separate one. They also have to make available to all interested parties all necessary emission and maintenance information. And then the quotations are mine, and that's where they're saying at a reasonable cost. And the reason I put it in quotations is because you have these multi-million-dollar attorneys that are defining what is a reasonable cost. For most shops, they're going to be getting this through AllData, through Mitchell, and primarily what they're looking at here is if the manufacturer releases a technical service bulletin to the dealerships for a emissions-related item, they have to make that available to the aftermarket at a, quote, reasonable cost. To illuminate the MIL, because we're monitoring the catalytic converter, they're not going to wait until the catalytic converter completely fails, is as its performance degrades, when it reaches 1.5 times the federal standard, they have to set the DTC. Oxygen sensors, because they slowly degrade over time, again, as the oxygen sensor begins to deteriorate, or as its performance begins to deteriorate, when it gets to that point of exceeding the federal standard by 1.5 times, they have to set the DTC. They're also monitoring engine misfire. And this is going to be a continuous monitor where they're going to be, for the most part, watching it all the time. And then the comprehensive component, this is any sensor that will affect emissions. Task manager or diagnostic executive is the trip monitor. So what we're looking at on trip, you go out to the car, you turn the key on, you start it up, you start driving. So it's not just key on, wait a little bit and turn the key off. That's not going to be a trip. It's actually going to require some drive time. The task manager is going to run a sequence of tests on the different systems on the car. It's going to attempt to test each system one time. It's then going to record that the test has been completed. That's your readiness monitors showing when it shows complete, that means it completed the test. Doesn't mean the test passed. Whether or not the diagnostic test is passed, and this is going to be either pending codes or in the mode 6 that we'll talk about later. And then any fault identified is not currently active. And what you're looking at here is a problem occurs, it occurs a second time, turns the light on. When you shut the key off, the next time you start the car up, the light is still on. That's now a history code. It didn't happen on this key cycle. It may happen again on this key cycle, and then it would be current as well as history. Pending code on most of the systems that the trip monitor or diagnostic executive is going to run it is going to require 2 consecutive failures. Now, what this is going to be is, let's say you have a catalytic converter that's just beginning to fail. And on my son's Jetta that he was driving, his catalytic converter was right at this point. He'd be driving along, and he has a long commute. His check engine light would be on for a few days, and then it would be off for a week, 2 weeks, a month, and then it would be on for a week, week and a half, and then it would be off. And he drove it for a couple of years like this. And each time that I checked it, it was his catalytic converter. And what would happen is, diagnostic executive runs the test on the catalytic converter. It fails the test. It's not going to turn a light on. It's now a pending code. The next time he starts the car up, drives it, it runs the test. If it fails a second time, now the light comes on, P0420. Drives the vehicle, runs the test, passes the test, light stays on. Drives again, runs the test again, light stays on. Runs the test, passes the test, but the light's going to stay on. The third drive, it runs the test. Now it passes the test, shuts the light off. It's no longer a current code. It was something that happened a while back. And he may drive it if he drives it for 40 more times and it passes the test for the next 40 drive cycles. The code will clear out of history. But if it fails 2 times in a row, the light comes on. While the light's on, if it passes 3 times in a row, the light shuts back off. The operating conditions at the time of the failure, in other words, can we run this test on this drive cycle? This is not how everybody does it. This is a typical drive cycle. Let's say that you're living in an area where you have to pass emissions. You want to take the vehicle out and get all the readiness monitors to set to complete. And this is the problem that technicians will run into. But the customer brings the vehicle in. They've been driving around for the last 18 months or last 12 months with the check engine light on. Now they have to pass emissions. So they take it into a shop and they find that, hey, the oxygen sensor is bad. So they replace the oxygen sensor and the customer saying, hey, my tabs are due tomorrow. I have to get it to pass emissions. Now you have to drive the vehicle and you have to get all the readiness monitors set to complete, or at least most of the readiness monitors set to complete. So here's your drive cycle. 1, the engine has to be cold. It has to be less than 120 degrees or 122 degrees. That's your 50 degrees centigrade. You're going to start it up, idle it, 2.5 minutes with the AC on, with the rear defogger on. Now, shut the AC off, shut the rear defogger off, accelerate up to 55 miles an hour at about a half throttle. You can hold 55 miles an hour for 3 minutes, then take your foot off the throttle, allow it to decelerate down to 20 miles per hour, don't hit the brake. Get down to 20 miles an hour, now you're going to accelerate at 3/4 throttle up to 60 miles an hour. You're going to hold 60 miles an hour for 5 minutes. You can't take your foot off the throttle and back on, so you can't accelerate, decelerate. You have to hold a steady cruise. Then, after 5 minutes, take your foot off the throttle, allow the vehicle to decelerate. They're saying if you can do this in 12 minutes, you can get all the readiness monitors set to complete. Here in the Seattle area, in the Puget Sound area, between the hours of 8 and 5, there is nowhere that you can do this drive cycle without somebody getting in your way or you getting in somebody else's way. It's impossible. Most of the time, I can take a customer's vehicle out or I can take my vehicle out and I can get most all of the readiness monitors except 1 or 2 to be able to set, even with other traffic around, as long as I get to a place where I can hold a steady throttle. There's 2 things about the trip. 1 is, what is the purpose? The purpose to get all the readiness monitors set to complete. 2, there is a minimum requirement for the trip, and that is key on, engine running, and some drive time. The drive cycle or the drive test or whatever name you want to put in there, each manufacturer, the engineers that work on that particular system, they may do that drive cycle a little bit different. It is going to vary with different manufacturers at different times. 3 different types of tests the diagnostic executive is going to run. The passive test is where it is just sitting back and watching what's happening. On the active test, the diagnostic executive is going to take control of the fuel trim. It's going to force the system 10% rich or 10% lean. It's going to run a test. The person driving the vehicle is going to have no idea that this is happening. It's a test that's going to run in the background. On a rare occasion, there will be an intrusive test, and this again is where the diagnostic executive is going to take control of something, and it is possible, unlikely, but it is possible that the person driving the vehicle may feel this test. Any sensor on the vehicle that can affect emissions up to 1.5 times the federal test is going to be monitored in a comprehensive. The computer is also going to monitor some of the systems, not necessarily a sensor, and the example I'm giving you here is the thermostat. If an engine is running cold all the time because the thermostat is stuck open or the thermostat opens too soon, it will set a code for the thermostat. Cold engine, they go into a fuel enrichment, that's going to affect emissions. But we have upstream oxygen sensors, those are the ones in the manifold, or real close to the manifold. Downstream is the ones after the catalytic converter. They're going to heat the oxygen sensors, so that's our HO2S for heated O2 sensor. They begin to work about 600 degrees. If you have a prolonged idle period, the oxygen sensor could actually cool back down. When I'm talking about the oxygen sensors, I'm not talking about the air-fuel ratio sensors. And in this presentation, I'm always going to be making reference to the oxygen sensor that's going to generate a voltage of 0 to 1 volt. The air-fuel ratio sensor is going to do the same thing the oxygen sensor does. In fact, it's still a zirconia sensor. It's just going to do a faster job, a better job, but it doesn't have the variable voltage like the heated O2 sensor does. It uses a variable amperage. When you start the car, diagnostic executive is going to look at the coolant temp. It's going to look at the ambient temp. It knows what size the engine is. It knows how much heat's going to be coming out of the engine. And it wants that sensor to get active within X number of seconds. If the oxygen sensor takes too long to come up to temperature, it may set a code for the heater circuit, or it may set a code for the oxygen sensor, but that's your time to activity. The response time, this is going to be an active test. That's where the diagnostic executive, without telling the engine computer, is just going to take control of this. It's going to force the system 10% rich. O2 sensor voltage is going to come high. It's then going to go 10% lean. It's going to watch how long does the oxygen sensor take to switch from rich to lean. And that's going to be milliseconds. It's then going to go back 10% rich. How long does it take the oxygen sensor to respond? Lean to rich. Again, number of milliseconds. That's where it's going to be catching a lazy O2 sensor if it just can't make the change as quickly as it needs to. It's also going to look at switching frequency, which is our cross counts on the scan tool, if that shows up on the scan tool you're looking at. On the switching frequency, this is the midpoint, 450 millivolts. If the voltage goes down to 300, up to 600, okay, there's it crossed the 450 millivolt, going from 600 down to 300 across the midpoint again. There's a standard for a particular engine, particular temperature, operating condition. It should pass X number of times in a second, second and a half, 2 seconds, whatever the engineers decide to use for that particular test. They compare that to what's stored in the PROM and pass or fail. So again, the time to activity, reaction time for lean to rich, rich to lean, the cross counts, that's not continuously monitored. That's going to be checked one time on each test drive. When it goes to check that, lean to rich, and you all of a sudden take your foot off the throttle because the car in front of you stopped and it interrupts that test, it doesn't attempt to run the test again. It stops the test. The test just won't run on that drive cycle. Catalytic converter, any other tests that depend on that sensor for the testing, it's not going to run those either. This is looking at the ability to maintain stoichiometry. And what we're looking at is our ideal air-fuel ratio, which you're going to hear people always refer to, that is 14.7 parts air to 1 part fuel. If you have gasoline, yes, it is 14.7 parts air to 1 part fuel. If you have 10% ethanol mixed in with that, well, now you're closer to 14.5 parts air to 1 part fuel. Short-term fuel trim, its purpose exists to watch the oxygen sensor. If oxygen sensor voltage goes low, short-term fuel trim percentages start to rise up. If O2 sensor voltage goes high, above 450 millivolts, short-term fuel trim numbers or percentages go low. Literally what it's doing is it's increasing and decreasing the injector pulse width to add or decrease fuel to compensate for the rich or lean condition. Long-term fuel trim is watching the short-term fuel trim, and as the short-term fuel trim is going rich, lean, back and forth like this, as it's going to positive numbers and negative numbers, long-term fuel trim wants the average of that to be 0. If the average is not 0, so if the average is 5, meaning we're adding fuel compensating for a too lean condition, long-term fuel trim is going to go positive 1. Watch the average and continue to climb until the short-term fuel trim average is back at 0. GM used to give you this information prior to OBD2, but GM called short-term integrator, long-term they called blockline. GM short-term and long-term fuel trim, they use the number 128 as a center point. Any number less than 128 was compensating for too rich. Any number greater than 128 was compensating for too lean. OBD2 made it easier. Most everybody uses 0, so any positive numbers compensating for a too lean condition, any negative numbers compensating for a too rich condition. The diagnostic executive or the task manager is watching short-term, long-term fuel trim averages. When the numbers get too high, it is going to set a code for either lean or rich, whatever it is. When the vehicle comes in with one of those codes, either too lean or too rich, now you need to figure out if it was too lean. Do we have a vacuum leak? Do we have a mass airflow sensor that's going bad? Do we have dirty injectors? Do we have low fuel pressure? Whatever is going to cause that condition. Codes do not tell you what the problem is. They just tell you where to look. We're going to stop at this point here. On our next video, we will start talking about the catalyst deficiency.